Well, hey everybody, welcome back. It's day 2. Hopefully day 1 went for you without too many technical glitches. Yeah, online learning can get interesting. So we're going to move on. We're going to look at variables and categorical graphs today. This can run a little bit long. I would suggest that you speed up the video if you feel like you can get through it more quickly. I am going to, in this recording, not pause to give you time to write, so it's up to you to do the pausing. Also, if you feel like it's just too much writing for you, then I would go ahead and go into the notes section, print out the PDF of this presentation, and then you can fill in whatever details you feel like. Let's go ahead and start. So this is what we're looking at today. We're going to start out with some terms. First one being statistics. I think everybody has a preconceived idea of what that is. Really all it is the science and art, interesting word, art, of collecting, analyzing, and drawing conclusions from data. So you notice that it's kind of seems imprecise to use the word art. Mathematics typically isn't an art form. It is a method to get exact answers. Statistics is a big departure from that. So we're going to get what we think is right based on best practice and probability, and then hope for the best. We're trying to find patterns and meanings within populations. Populations are an important concept. If you have an initial question, what's the average height of a teenager in the US? Well, there's a whole lot of teenagers in the US. So if you took a clipboard and decided to go out and measure all of them, you would never get to the end of it. So you might just throw up your hands and say, this is impossible, there's no way to know. Well, rather than abandon that quest for knowledge, we use statistics. So we will get what we would consider a representative sample from the population we're interested in, get measurements from those individuals, and then draw conclusions which we would hope would infer back to those populations. Now here's the issue. Suppose with a room full of teenagers that I've got right now, I decide to randomly pick, like, say 10 of you, and then measure your heights, take an average, and say, okay, well, I'm guessing that the average for all teenagers is this particular number. The problem comes if I were to take a different group of 10 and come up with an average for that group. Can you guarantee me it'll be the same average as I got from the first group? See, it's probably not going to be the same. It would be a miracle if it were. So statistics is about dealing with that variation. Data sets just aren't the same from group to group. So measurement is an imperfection. Statistics is an art form that allows us to make some sense of this imperfection. So some vocabulary. Individuals will be objects described by a set of data. They can be people, animals, bricks, cars. Anything that we need a measurement from is going to, we're going to have to get individuals from within whatever group we're interested in. When individuals are people, we will refer to them as subjects. So population will be the set of all possible individuals rather. Typically populations are big. Sometimes they're not, but they're usually so big that we have to use statistical methods to draw conclusions about it. So we'll use data from individuals to make generalizations about populations. And then the idea of a variable will be an attribute that can take different values for different individuals. So let's look at variables. All right, categorical variable will name categories. It'll answer questions about how cases will fall into those categories. So gender, for example, men and women. The interesting thing about categorical is that you can't assign any more importance to one category than to another. So when we're looking at gender, we're just looking at variance of human beings, right? Can't really say that men are better than women or women are better than men just as an overall thing. You know, men may have more of this attribute than women, but it doesn't make men more important or anything of that nature. Race, same thing. Political affiliation, Democrat, Republican, Independent, Green Party, just where do you fall? Now, a quantitative variable basically will be for a single category. Like we've got an example later on that's AP tests that people take. Number of them. That's it. That's the only category. We're not asking about other kinds of tests. It's just AP tests. So these would create quantitative data. Quantitative variable is a counted or measured variable that has units and answers questions about quantity being measured. For example, income, all right? Height in inches, weight in pounds, running speed. Everybody's got a different running speed from everybody else for a particular distance. So that would be measured and fall under that particular category. All right, your quantitative variables break down into two types. One is discrete. And what I want you to do is picture a number line with integers on it. Let's just say whole numbers from 0 on up. And your data will fall only on the whole numbers. So if I'm looking at age in years, for example, I might have 14-year-olds, 15-year-olds, 16, 17, 18. I'm not asking for anyone who's 14 years and 4 months or 15.2 years old. I'm only asking for those particular discrete values. So that produces discrete data. And sometimes things that are continuous, that's the other version, can end up being discrete depending on how it's rounded. So when I give you a test grade, it's not going to be 92.3. It'll be 92. That would be discrete. All right. Discrete random variables are items which can be counted. Continuous, picture that number line again, and I'm not restricted to just the whole number values now. I can put any kind of measurement anywhere in that number line. So, for example, GPAs, if they're unrounded, because we could get a tie for valedictorian, in which case they go to the next decimal place to break the tie. Task completions time. If I'm timing something, that stopwatch can stop anywhere. It's not going to necessarily stop at 8 seconds. It might be 8.8 seconds. Blood pressure, again, we do report it in whole number values, but it is a measurement, and it's just that we're kind of randomly choosing how to report it. But since we're measuring it, that would make it continuous. So continuous quantitative variables are items which can be measured. Oh, just real quickly while I'm thinking of it, an average is a continuous quantitative variable, because if you average something for grades, for example, it doesn't mean that that average actually exists as one of your grades. It's just a combination of all the grades. So if you see something that's an average, that's going to be continuous. The last type of variable will be identifier. These are categorical variables with exactly one individual in each category. So social security number, your social security number and mine, if mine has a bigger value to it, that doesn't matter, because we don't do social security numbers as any more than a tag or a way to distinguish from you to me. IBSN number for books, they just distinguish one book from another. FedEx tracking numbers, driver's license numbers. My room is 2216. My neighbor, Miss Shepard, is 2217. Her number is bigger. That doesn't mean her room is better or larger or anything. It just means if I direct you to one or the other, you'll be able to find it. So we don't analyze these. Sometimes you can get a categorical variable that is beyond being just an identifier. It may just have one individual in the counts, just be aware that that can happen. All right, so just because your variables values are numbers, don't assume that they're quantitative. So Jersey numbers, zip codes, there's really no way to rank order those things in a meaningful way. So they just identify whoever possesses that particular number. So here's your breakdown. Categorical are just counts within categories. Quantitative split into discrete, which would be countable. Continuous, which would be measurable. And identifier. Okay, so here's an example that I'm going to ask you to work on real quickly. Your Census Bureau collects data from 3 million households as part of the American Community Survey. Here we have a table to display some of this particular data, and it's broken down into household. Here's some numbers that apply to the household, region, number of people within the household, time that they've lived in the household, how they responded, what the income is within the household, and then internet access. All right, so you've got what type of variables would apply. See if you can figure out each of these bolded headings, what type of variables they are, and pause your pause the video. All right, we're back. Let's see how you did. I typically have trouble with the household. Really, every household that they examine just gets an identifier number, so that is an identifier. Region, these are categories. Number of people within the household, these are quantitative discrete. See how they're countable? You could line them up and count them. Time in the dwelling in years, you see how they've put these into distinct categories? That would make it categorical. Response mode is categorical. They did round this, and it's not taking an average. They rounded it to the nearest dollar, so that's quantitative discrete. And yes or no for internet access would be categorical. You either fall in one category or the other. So how did it go? All right, I'm going to pause now. This is your attendance code for today, so go into assignments for 420 and open up that assignment, type in 6429, submit it, and you're done. So go ahead and pause this. Make sure you do this by 3 o'clock. All right, so moving on, a distribution. Now, this is a graphical display of the distribution, but this on the left is your distribution. It's kind of a chart that tells us what values the variables take and how often it takes them. This is about Spotify data, and they're looking at for out of a sample of 100 by age, for Beatles listeners, and they kind of came up with these arbitrary ages, but you're either in this category or this one or this one or this one, so it's categorical, and these are the counts for them. So here it is. This is a distribution for this categorical data. Here's another one. This is a frequency table. That's another way to call it for a categorical variable, and this is for shipping method. And here's your categories. They either ship by ground, second day, or overnight, and here are the counts within the categories. So you want your frequency distributions to look good so that people can understand them. Now we could put another column here for percent or proportion. It just doesn't happen to be in this one. This is for quantitative data. We only have one category, and this is for number of AP exams taken by student, and this is quantitative discrete because Doug took 2, Carl took 4. You can't take 4.5 AP exams. So here it is. This is a frequency distribution for this particular quantitative data, just one category. Now we could average these up and we could make this into continuous, but that's not what we're seeing here. All right. So going back to categorical variables, here is one way to display them in a graph. Graphs are great. They are worth 1,000 words in a picture, and you need to produce them for the little amount of times I'm going to ask you to do it in a manner that will convey meaning. So they need to be complete, they need to be neat, they need to be professional looking. This is a bar chart, and bar charts stay true to the area principle. I can tell you immediately what's going on here. We're looking at the frequency of Titanic passengers by class, so we need a title. And here are the different classes, and they're broken down by category, so you need that. And an overall axis label, and these are the counts. See, frequency means counts. Now, I can look at this, and my eye's going to respond to area. There are more crew members than any other group. The fewest are the second class, and so on. Okay? Now, keep in mind you need to keep these bars separate, because if they touch each other, you know, if this butts up against this, which butts up against this, you're telling your reader it's only one category. But these are all four separate and distinct categories, so don't let them touch. Put this on graph paper. If you don't have any, Google it. There's a million places to print out graph paper. When you see my keys, they're all done on graph paper. You can actually pull it off on notebook paper, but you need a straight edge, right? So, straight edge. Title, labels, decent scales, decent presentation. Now, if you look at this one, it looks like it's exactly the same as the other one, except we converted to percent. So we took the total number of all of the passengers and divided that into each of the classes, and we got percentages. So this axis is different. Now you can report this as 0.1, 0.2, 0.3, 0.4. Don't go up to 100%. Why? Because your biggest percentage is below 40 or at 40. And if you just go higher than that on your vertical axis, it'll smush all of these things down. And we don't want that. All right? So this is a relative frequency bar graph or bar chart. Relative frequency is the same as percent. Same kind of presentation, same kind of formality is required. All right, here is a way to do comparisons. We are comparing educational attainment for adults 25 or older in 2 different years. So anything in blue was gathered up in 1992. Anything in red was gathered up a few decades later. And you can see meaning here. It looks like we're seeing a bump up here in educational attainment in the later year, right? So we've got a lot more people getting as high as high school, right, or less. But once you get beyond that, we're really kind of exceeding in our college or our post-secondary for the later year, right? Again, title, labels, this is relative frequency, it's in percent. So yeah, I can see right away some meaning in this just by how well it's being graphed. All right, a pie graph is pretty common. You may have done these when you were in junior high or elementary. You just take a circle, find the center, and divide it up into sectors. The sector area is going to be based on either the counts that you have for your categories or the percentages. I am not going to ask you to do this. This takes a long time. You definitely have to account for everything so you can cover all 100% or 360 degrees or all the counts. You may just have to interpret them, but it is something that you see quite a lot, the pie graph or pie chart, and you know the slices just correspond to whatever your categories are. All right, so misleading graphs. I'm going to go ahead and switch over and play you one of these. You might want to play the other one when you get a chance. So let's see if I can pause this. Hold on a second.
Hello and welcome to a video presentation on misleading graphs. Here's what you'll learn. How to identify and analyze misleading graphs. First of all, what are misleading graphs? Well, any graph that distracts the reader from fully understanding what he or she is viewing can be considered misleading. Here are some examples. Graphs with no title. Graphs with no labels on the axes. Graphs with no key when a key is required. Graphs with a vertical axis that doesn't start at 0. Graphs with different sized graphing icons or bars. Graphs without equal intervals on any axis. And graphs with a broken or squished axis. Now let's take a look at some examples of these misleading graphs. Here's a graph comparing the popularity of the PS3 to the Xbox 360. And they're using the game units as icons in the graph. Looking at just those icons, it looks as though the PS3 is 3 times as popular as the Xbox 360. But this is misleading because the vertical axis doesn't start at 0. It starts at 44.5%. And in this survey, 49% of the people said they preferred the PS3, and 46% of the people said they preferred the Xbox 360. Now, to be sure, more people did say they liked the PS3 than the Xbox 360 in this survey, but that's only a difference of 3%, not 3 times as many people. So that's why a graph whose vertical axis doesn't start at 0 can be misleading. Let's take a look at another example. Here are the math scores from 2003 for 4 elementary schools. This is a misleading graph. Look at the vertical axis. It starts at 299, not at 0. Because of that, it makes it look as though the kids at Overachievers Elementary are 3 times as smart at math as the kids at Dullsville Elementary. Let's remake this graph properly. Here's the same graph using a correct scale. We start at 0 at the bottom. We use equal intervals all the way to the top, and when we fill in the bars for each school, we find there really isn't much difference in the math scores at all. Here's a misleading graph with different sized display icons. We're comparing the average ticket prices for 3 sporting events: hockey, baseball, and basketball. Now, while the icons may be fairly representing their associated sport and ticket prices, it's the size of the icons compared to each other that's misleading. Look at the top of the basketball. That may very well be representing $38 to get into a basketball game. And the top of the hockey puck and the baseball may very well be representing $18 to get into one of those sporting events. But look at the size of the hockey puck compared to the size of the baseball. It's probably about 2 times what you would expect if they were in direct proportion to each other. So if you were to just look at the icons, you might think it's twice as much to get into a hockey game as to get into a baseball game. Now here's that same graph using bars and unequal intervals on the y-axis. Take a look at the y-axis. It starts at 0, but the first interval is a group of 20. It goes from 0 to 20. All the other intervals are intervals of 5. This is misleading. Because we didn't use equal intervals, it looks like tickets to basketball games are 4 times as much as to get into a hockey or a baseball event. A better graph would use the same icons or bars for each sport and have equal intervals going up the vertical axis. Now we can do a fair comparison between ticket prices for the 3 sports. Here's another misleading graph with a broken or a squished y-axis. This is the women's long jump, and the distance is on the vertical axis and the 4-year increments are on the horizontal axis. Because we have a squished axis, the very first interval represents 6.9 meters when all the other intervals just represent 0.2 meters. Because of that, we're going to have a misleading graph. It looks like there was a huge difference in the women's long jump distances between 1984 and 1988. If we actually made this graph not squished with the 0 at the bottom, it would look like this. And yes, there is a difference between 1984 and 1988, but it's not as dramatic as the misleading graph made it look. Congratulations! You've now learned how to identify and analyze misleading graphs.
All right, so we're back. I hope you found that interesting. The other one is real interesting too. In fact, if you just go on to YouTube and do a search on misleading graphs, there's a number of them, and there's a whole lot of ways. Mainly, you just don't like those picture graphs, and you don't want to play games with your vertical axis in order to make things too exaggerated. So let's get back to this, and let's see. All right, this is the last thing we're going to cover today. We're going to talk about segmented bar graphs. And these things are kind of a rectangular version of a pie graph, pie chart. What you do here is you take your categorical data, categorical values, and take them all the way up to 100%, and then divide into whatever percentage your different categories happen to be. Now you do need a legend, see over here, so that you can tell which one's first class, second, third, and crew. If you don't want to do colors, you can just do cross hatches and slant lines and whatever you have to do in order to distinguish between categories. So it has to be percent so that you can compare different counts, because I don't think we had the same number that died as those that lived. And yeah, so when you get this done, you can look at it, and it's got a pretty dire sort of meaning to it. There were more of the crew that died than lived. There were more of the, or proportion rather, there was a bigger proportion of the third class passengers who died than lived. So it looks to me like if you're in the first or second class, see, here's the ones who died, and here's the ones who lived, that your odds of surviving this disaster were far greater. So it's a great graph, and I'm going to show you an example in a minute that may make constructing it a little easier. So, and again, this is just telling you you have to do percentage so you can compare groups of different sizes. But don't forget all of the requirements that you need for any graph. You need a straight edge. You need to have labels, right? You need to have a decent scale, and you need a title. Okay, so let's see what's next. All right, your homework is going to be in your packet. Types of variables will be the first page of it, and then categorical graphs will follow in the same worksheet. And don't forget your urgent items for AP statistics. Many of you got that done. That's great. I know I'm leaving that open for a while, but that's mainly because I get people switching back and forth. You know, in the class, out of the class, whatnot. I get late arrivals. So I do need to leave it open, but if you're enrolled and you're sticking it out, get this done quickly, because if you don't and you need a calculator, you may not get one. So let's go on and look at this last thing I wanted to show you. This is an example that's in your packet, and it would be nice if we could just take class time to do it, but it's a little easier to do it in person than it is through virtual. So what we've got here is some data. It's categorical, and it has to do with the January 2007 Super Bowl. So they asked 1,008 Americans 18 and over if they planned to watch the game. For those who said they did plan to watch, they broke that down into whether they'll watch they're there for the commercials, or if they won't watch at all, right? So I'm sorry, let me just back up. This is tuning in just to watch the game. Here's the males, here's the females. Here's the ones that are tuning in mainly for the commercials. Here's the males, here's the females, and these are the folks that won't watch. All right, so I think we have this right. So they actually interviewed more females than males, and here's your total of 1,008. Here's your subtotals. So this is a really good frequency distribution, and so I graphed it two different ways. All right, so here's Super Bowl by preference. Maybe I can make that a little bit smaller so you can see it a little better. And I did a side-by-side. So here are the ones watching the game. Here's your women, here's your men, are tuning in just to watch the game. Here are the ones that are tuning in to watch the commercials, and here's the ones that won't watch. I did relative frequency, And it looks like more men, or a bigger proportion of the men, are tuning in to watch the game than women. And a bigger proportion of the women are tuning in just to watch the commercials than the men. And they're not too different for not watching, but it looks like the females are proportionally a little higher than the men. All right, so there's a side-by-side version. This is, I'll make that smaller again. This is the segmented bar graph. And so I do have a legend here on both. Make sure you have it. So here's the ones that are tuning in just to watch the game. Here are the ones that are tuning in just to watch the commercials. And here are the ones that just won't watch at all. And the way I did this, of course, go up to 100% men and women. And I went ahead and just did the ones tuning in order just to watch the game. That's their main interest. So here's the proportion of men. Here's the proportion of women. Again, it's showing a bigger proportion of men. And then tuning in to watch the commercials. There it is, more women than men proportionately. And then finally won't watch. In order to construct this, what I did was I did the watching the game first and worked from the bottom up. And then I did won't watch next, rather, and I went from the top down, which is kind of easy to do. And then what was left over was tuning in mainly to watch the commercials. And if you have just 3 categories, it's super easy. You can do it with 4. You're just going to have to split these 2 in the middle to accommodate the other 2. But this went together really quickly, and it looks good. It's on kind of a grid, as is the other one, and these are considered good graphs. I got my labels, my titles, my scales, my legend. I did it neatly with a straight edge, and that's all I ask. So that'll conclude for today. Thanks for watching. Thanks for participating. Knock out the assignment. Come in Friday. We'll have made it through our first week, and we'll address questions and wrap up these categorical graphs tomorrow. So, goodbye for now.